Video time, yay! Anyway, back on the draft science stuff. I'll respond to the comments over here first. Yeah, I'm just using this a little different format than the usual. I don't know if I like it actually. I mean, this left to right thing. I suppose I could just move this over here. That might be more convenient for me anyway. And then we gotta read more of these and such. Ooh, 84 lines, that's an awful lot. But anyway, okay, so the Hospital Day made a video. It's sort of interesting. Went into more of these Bell theorems and whatever, all these equations and stuff. I don't know if he really didn't really help me too much in understanding them, but it did make me think. And concept I came up with was interpretation. And in the sense that there's a language of the transmission of information. So as I speak, there's things happening. First, my brain does something. It sends electrical signals to my larynx. My larynx vibrate. The vibration and air is pushed through the vibration to migrate the speed of sound movement from down here, resonate it through my mouth and out, and then into this atmosphere where it has to travel rather slowly to the camera. Then the camera does its end. So it's an interpretation, and through all these steps there are interpretations. And what's really happening is an interaction between electrons and photons, substantially, I think. That's sort of what's going on, is that it's an interpretation of what's being sent originally in one form is being converted into another form. So it's like a language interpreter or software interpretation. It's changing it into a different format and then reconverting it back into a format again. So it might look this way when you look at it after we've looked at it. When we're looking at a sine wave, are we really seeing what gets transmitted? Is the wave transmitted as a sine wave, or is that how we see it once it's been reinterpreted by electrons and electrical hardware? And so I'm going to argue that the communication of the information through this medium of the atmosphere, through this mechanism of sound, is happening through physics. It's happening on the level of physics, and it's not simply a migration of molecules. It is it's riding on a function within the molecules already existing. They're already in a state of harmonious vibration, and when you introduce a new vibration, a new stimulus, you change their electrical dynamic, you change their vibration, and it is conveyed through the substance, much like an electrical current would be conveyed. And like electricity, sometimes it moves rather slowly depending on the medium, depending on the quality of the conductor. And you could just argue that the atmosphere is a slow conductor, not a great conductor. Alright, anyway, that's the back story. So so in these comments I don't see anything saying here's a demonstration of sound produced with no speed of sound mechanism. I don't think these arguments don't prove speakers don't vibrate at the speed of sound at all. So I don't think they do it. They're not going to change my mind, and they're not disproving my hypothesis. So anyway, let's go through it. Heat travels more slowly than sound because the molecular motions associated with heat are random. So that argument, basically I made the argument that the heat doesn't move anywhere nearly as fast as sound through the atmosphere, and technically if it's just movement of molecules, it should. And so this idea of random, it's not that random. Light bulbs aren't random. Certainly if I turn on my gas stove, there's nothing random. There's a huge amount of energy produced at that flame, and there's no way, if I let it go, that it would be transmitting anything detectable, any detectable substance besides light, photons, that would go very far into the atmosphere. So there's nothing coherent about the disruption, even though it is very directed. I can certainly direct heat. I can certainly put a parabola around the heat source and force the heat into a direction, and so you can't use that argument, in my opinion, to explain why heat moves so much slower than sound, and how it doesn't have anywhere near the durability in maintaining its integrity. Whereas these associated with sound are directed. Yeah, well, it's more than directed. It's affecting molecules on a different level, and I'm going to argue it's because it's affecting them on the level of a sonic boom, a pressure wave that affects the core of the molecule, not the periphery of the molecule. It's a vibration to the core. Anyway, when I guess I could draw some sort of picture of it. I mean, it's so hard because molecules are kind of complicated, and it's hard to just do a simplistic drawing of one and say that's it. But the idea is that you have this atom, and it's always vibrating. So this position, you could just do a dotted line, is always changing at certain frequencies. Maybe the nucleus stays the same, and maybe just the rings of the orbits change through this vibration. And so you can have movement that would cause maybe a nucleus to move with the atom, or maybe the nucleus doesn't move, and the only thing that vibrates, the only thing that moves is the eccentricity of the orbit, the shape of this orbit. And there might even be a third level of interaction that might just be based on these photons that one assumes exist between the associated atoms. They are in communication with each other in atmosphere. A type of tension is established between them, in that they do end up having these associations. And so there's these levels of communication where you can communicate through the photons that might be connecting two atoms or associating atoms. You could communicate by changing the orbit of the electron, in terms of displacing it, or you could communicate by actually moving the nucleus. So my argument is I'm not saying which one is affecting it in this video. I mean, I could figure it out, I suppose, if I think through that, which one is most likely. But sound is obviously very durable, so I would argue that it's likely affecting it more in this, at least this electron level, and where heat might be just affecting it because of the slower movement on this more photonic level, so that molecules essentially roll around each other instead of actually smashing into each other or pushing each other, that they end up just kind of rolling on a cushion of electromagnetic force, photonic sparks of you can almost say static electricity kind of forces that would be made of photons that are connecting them, that kind of thing, weaker forces. Anyway, when air molecules hit the rising diaphragm, their speed not only gets a boost, but they get a boost in a particular direction. Well, again, you can't argue that heat isn't directional, because it can be very directional. The point is, it has no durability over distance. So unlike sound behaves not as if it was frictionless, but it seems like it has a lot less friction to its propagation. It propagates without losing its authority as quickly as heat. This means that there is an overall transfer of momentum that occurs with sound that doesn't occur with heat. Well, you say so. Again, you haven't demonstrated. You're not, obviously you can't do that in this single paragraph. But you haven't explained how there is a difference in the affecting, the jiggling of the molecules between heat and sound. In my argument, what makes sound distinct is the speed of the jiggle, the speed of the extra frequency, and that speed is related to the speed of sound. Furthermore, molecules that make up the air are electrically neutral and non-magnetic. Well, anything electrical it can be magnetic, as certain other videos have demonstrated, hospital days for example. The average distance that an air molecule travels before it collides with another molecule is around 50 nanometers. Again, colliding, I think, is kind of bogus terminology. I think the movement is not once saturated, okay, without turbulence, that much movement isn't taking place, and clearly sound isn't greatly affected by turbulence. It takes quite a strong wind to knock a sound out of propagation. So it tolerates a tremendous amount of turbulence. The size of an oxygen molecule is about 1.1 nanometer. That ratio of 500, which means that air molecules are far apart from each other, other than only meaningfully interact when they collide. Again, you can say they're far apart from each other, but obviously they are quite resistant to further pressurization. So they're clearly under pressure. They clearly don't like each other much, because obviously they're maintaining distance even though they are under pressure. So they're not combining or locking or doing something else like that. But clearly, even at a long distance, they have already decided they don't want to be any more compressed. They resist compression. Interesting enough, the average speed of an air molecule is 1,160 miles per hour. Anyway, says you again, which is greater than the speed of sound. Maybe this is what you are referring to. I don't see how it could be possible that I'm referring to that, but a single molecule, obviously moving at the speed of sound or faster, wouldn't be capable of creating a sonic boom, in the sense that even if it did, it would be so small that we wouldn't be able to perceive it. So that would be my argument there, that the mass of the thing moving at the speed of sound has to be sufficient to create a sufficient sonic displacement. So it has to displace enough molecular air for that to happen. But again, this movement at 160 miles an hour, I don't know who measured that, and I doubt that includes all the vibrations that the molecule possesses. But keep in mind that this is the average speed even when there is no sound waves traveling through the air. Again, I think that is. I think that's just bullshit, so I don't know where you got that number from. I don't know how to calculate something like that, and I don't think it has anything to do with the real way that molecules interact. They tend, like everything else, to stay where they are. It's like there's glitter in here, right? But because the light bulb isn't quite directed enough, it's not moving right now. But like, I create that turbulence up there, and it's all going to start stirring the stuff up. And yeah, it should show up. There's the little bastards are showing up. There they are. And so that turbulence will just keep working, and we know that that'll all even out. And that's what it wants to do. The evenness, is the native condition, is to maintain a condition, and to resist some sort of change in condition, which is relevant in the sense that although there are movements, molecules are moving, I think they're doing more vibrating than they are moving. I mean, moving in terms of going great distances. There certainly are currents of cold and warm air constantly moving, but that movement isn't the movement that is the substance of a molecule's movement, which is the vibrating it's doing at specific frequencies related to its size. Anyway, so the other guy says, I don't mean to be an asshole. I really agree with you on a lot of subjects, and that's when you don't see or hear me. But on this particular subject, ... Well, whatever. I'm not asking you to agree with me. I'm just saying your counter argument is crap. So you got to make it better. If you're going to say this is the truth, I think you're going to have to do a better job of it. I'm not an expert. Well, you're talking like you are. But I do have a more than basic understanding of the physics and mathematics of waves and sound. You seem to have so many misconceptions about this particular subject that saddens me. Well, I think it's just a bogus way to put it, okay? I mean, you can call them misconceptions, but I don't think you've proven any of them to be misconceptions. And all you're doing is talking from some kind of status quo, like we know what the truth is and you're wrong. Bullshit. And I'm calling bullshit on that. And that saddens me, okay, that you'll sit there and presume yourself correct without making an argument demonstrating yourself correct or demonstrating me to be wrong, and you're not doing that. And you're the one that came up with this bogus idea, okay, that a wave of frequency, okay, this thing here, that somehow, because you have a length, that this means that you are saying the amplitude of the wave is created at a known speed, okay, that you know exactly how fast this amplitude is reached. And my argument to you is no, that's what you see on an instrument, okay? So you're saying that I'll calculate the distance of this frequency and establish that that is the speed of reaching peak amplitude. Well, in the first place, even if it was a sine wave, you'd have to cut that in half because the peak amplitude is reached in the first half of the wave. So you're right there, you'd have to double your frequency in the sense that you have less time for your amplitude to be reached now, and time in this equation equals speed. So I've cut your time in half right there, and I'm still going to argue that the real wave function here is something that probably looks like this. Alright? And that's the real form of the wave. And what you're seeing is the interpretation of the wave after it's gone through atoms again. Again, this is getting interpreted. Okay, it's being sent and resent and resent through different forms of matter, and through each one of those interpreters, okay, it's changed probably. But I mean, certainly that's like shorthand in English. You could cut this, you could cut the physics of this wave into simpler numbers, like just an amplitude, a peak height. It would be one piece of information, and that might be enough, and frequency. So if you sent the information of amplitude and frequency in some other form as a peak and as a duration before the next peak, theoretically the rest of the wave could be artificially created in the interaction with the atom. And this is all you're really doing is transferring the information. You're just transferring the peak, the amplitude information, and the frequency information. And so that can be transferred maybe as a photon, or in how a photon is affected in its behavior. So you can't demonstrate, you certainly can't defeat my argument that, if I change this pitch, I change the speed that this amplitude is reached. And you're not making any argument that you have proof that this isn't, that this amplitude is not reached by exceeding the speed of sound. Especially, you don't even know that in the progression of this, getting to this amplitude, getting to this peak, climbing this mountain, say if it was a mountain, you haven't proven that this speed is consistent throughout, that the climber moves at the same speed here, and the same speed here, and the same speed here. Maybe he goes very fast at first because he's not very tired, but then by the time he's getting to the last, when he's getting close to the top, it takes him an hour to go 10 feet, where he was moving at 50 feet an hour here. So you haven't demonstrated anything. So fuck you in this attitude. Your sadness. Screw your sadness. Anyways, here's a somewhat more in-depth reply. Yeah, well, I think I read it. I don't think I liked it. The big difference between gases and solids and liquids, well, that's what we're talking about, is that in gases, the molecules have enough kinetic energy to move freely. In solids and liquids, they are stuck together in one way or another, and they do not have enough kinetic energy to get away from each other. And it doesn't matter. In either one of these substances, sound still travels, and still travels through basically the same mechanism, just at a different speed. So obviously, how much the molecules, how free they are to move in random, not in random, but to be moved in bulk, in patterns of flow, their ability to flow, doesn't substantially change the ability of the sound to be transmitted. Obviously, a lot of flow in the air will knock sound out of the air or change its directionality, make it sound. You can make a sound seem like it's coming from behind you when it's in front of you, based on how much the wind is blowing. Anyway, then they are just vibrating in place, or vibrating and rolling loosely around each other. Well, this is stuff I know, thank you, but I don't need that. When they have enough kinetic energy, they bounce off each other. When they have enough kinetic energy, so that doesn't make any sense either. They don't have the energy. The energy is imposed on them. So when something else bumps into them, molecules in a gas aren't smaller or bigger. Well, I'm sorry. Okay, I think it's just bullshit to say they're not smaller or bigger. They are. Atoms come in different sizes. Okay, some atoms are big atoms and some atoms are little atoms. They have more kinetic energy. They're more free to bounce off of each other. Again, free to bounce off of each other has nothing to do with the fact that sound is transmitted through them, okay, through the mechanism that ties them together, not a mechanism that's allowing them to be free. Sound isn't exploiting something that they're free to ignore. Sound is exploiting a fact that they are connected. They do create a kind of tension between me and the destination, and the sound travels on that tension. Alright, temperature is basic. Temperature is basically just the average kinetic energy of the particle in a given substance. There is no directionality to it. Well, again, I think that's just to say that temperature doesn't have a direction, or that atoms aren't incredibly excited at a point of the creation of temperature or heat, I think is just absolute nonsense. So I don't know where to go with that. The tip of a flame, for example, there is an intense movement of the molecules, and yet they make no sound, and yet that movement doesn't have any durability, even though the direction is quite obviously in one direction, substantially. At a small scale, heat travels with seemingly random paths through a substance. Well, again, seemingly random. I think it's bullshit. There's obviously heat travels in patterns and directions based on the pressure created, right? cold and hot migrate past each other because of pressure. When you are creating sound waves, however, you are bumping a huge amount of particles. So you're saying huge. These tiny little speakers aren't moving that many, but they're moving them fast, and that's for sure. But again, to argue that a campfire isn't moving a hell of a lot more molecules is silly. In the same direction, hundreds of billions, literally. Well, again, I'm going to argue that some kind of high energy heat source, infrared light, for example, or something, it should be screaming in my ear, and it's not. You're creating huge compression waves compared to the random motions of particles we experience as heat. Well, again, you're saying that's random motion. It's not random. It has high intensity, high pressure points it creates. The difference is it doesn't move, the substance doesn't move faster than the speed of sound, and when it does, we hear it. We hear the fire crack when something in the fire explodes and moves molecules faster than the speed of sound. The air molecules are already moving roughly at that speed. Well, regardless, the point, whatever speed they're moving at, the point is they're not jolting them the way sound is. Sound is jolting them, hitting them with the right frequency, the right intent, the right acceleration. And that's the key point here, is the acceleration has to be fast enough to move the core of the atom rather than just displace its electrical field. Or vice versa. I mean, technically it could be the other way around, that sound affects the electromagnetic condition of the atom rather than the core. But I don't want to argue that part. I just want to argue the fact that speed is critical to the creation of sound. I am saying how fast the diaphragm is moving in a specific example. No, see, and then what I'm saying is that example is bogus. Because you're deducing it based on assumptions that I don't think are correct. I don't think you've established them as proven facts. I don't think you know how fast the amplitude of a given frequency is created, or I don't think you've either proven that waveforms are transmitted in the same condition that they're created in. That they are in fact interpreted through different manipulations in different matter. When they migrate to a different medium for transmission, there's all kinds of changes in how they may be structured. And what you're moving when sound is transmitted, I'm going to argue you're moving something that is affected by speed. Anyway, amplitude says something about the loudness of a tone, while frequency says something about the pitch. Now, I am repeating myself. And yes, I disposed of this crap. So you can repeat yourself till you drop dead, but that doesn't prove a motherfucking thing about the speed at which the amplitude is achieved. You haven't proven that going from here to the peak of the amplitude of a wave happens at something lower than the speed of sound. Sheesh. Alright. Okay, the air molecules surrounding your nail are already moving at the speed roughly of 450. Well, again, they're obviously not moving that fast relative to the rest of the environment. So you can say that relative to each other, they're moving at some sort of speed. But as a nail itself, it's certainly not moving at that speed. So that's bogus anyway. And my argument isn't about how fast the atmosphere is. Maybe the speed of sound is really 7,000 miles and that 6,000 of those are, 600 miles, let's say 7,000 miles an hour, and that 6,000 of that is being absorbed by the movement of the atmosphere in its native state. And it told me that extra boost, so it's just the extra acceleration that creates a sonic boom, and so that the real sonic boom only happens at 7,000 miles an hour. I mean, you can create a scenario like that where there's a pre-existing condition and you're only boosting the pre-existing condition another 750 miles, well, you're saying miles a second, or meters a second. So, yeah, but those vibrations aren't, you're counting vibrations as movement, and I don't know if those are the same things, right? I'm not sure of that at all. You are creating areas of higher or lower pressure, which in turn propagate through the air. Well, again, you haven't explained how the intensely high pressure changes created by temperature don't create the same kind of auditory disturbance. Air pressure. The molecules that fill up the void left behind are pushed in by the surrounding molecules. Remember that the molecules are constantly bumping into each other. It's not just about bumping into each other. Yeah, they're bumping into each other in an atmosphere of compression. So there is tension in the atmosphere. The atmosphere is a thick medium, and it's clearly one that the constituents, would be happy to be liberated. They don't like being this close together. Indeed, I don't think anyone is denying that. 1 cm of air has about molecules in it. To repeat myself once more. Well, again, repeating yourself when I already disposed of this argument is kind of bogus. So why don't you deal with me? Why don't you quote me and then tell me how you proved me wrong, where you didn't do any of such thing here. Repeating myself once more. Sound consists of pressure waves, which doesn't mean anything. The air molecules are already moving at roughly the speed of sound in random directions. Well, again, you're saying they're moving roughly at the speed of sound. That may be true. It's sort of irrelevant because they're obviously not creating any kind of disturbance, because their movement isn't mean interactive movement. And it's only through this interaction that something happens, and it's only when the interaction is significant enough to create enough of a disturbance that we can actually hear it. So maybe the interactions are enough to be creating little sonic booms, but single atoms, the sonic boom of a single atom is just too small to ever be heard. And you need a million of them, or maybe 10 billion of them, to actually create sound. The waves of pressure that make up sound, that originate from various sources and phenomena, are huge compared to single molecules. Well, again, I'm not the one arguing that single molecules are creating sound, so I don't even know why this should be of any interest to me. And I would argue that heat sources are creating huge volumes of movement, and that movement doesn't create sound. The wavelengths of audible sound waves won't go much smaller than 17 meters. This is huge compared to the 10 to the 19 air molecules that occupy 1 cubic centimeter of air. The wavelengths of audible sound, again, I don't care about audible. It's irrelevant to my point. I'm talking about what propagates through the atmosphere, in the form of these efficient waves that survive, that are durable and transmit through the atmosphere, and that have a source that I say can always be linked to something moving very fast, faster than the speed of sound. And I'm telling you that's what's happening in my larynx. I'm telling you that's what's happening. Let's go through it. The engine noises. What's making noise on the engine? Little teeny parts moving very fast. Alright. Gas molecules don't condense into a liquid or deposit into a solid because their kinetic energy or temperature is too high. They simply bounce off each other. This is basic physics. Well, duh, and I don't think I need you to tell me that. If you cool them down, they will begin to stick at some point. Well, again, the sticking is a lack of, stick is the wrong word to use, in my opinion. Because all you're doing when you take away the heat is you're taking away the some of the vibrating. You're taking away some of the bounce. You're taking the bounce out of them. Their elasticity, the rebound that's going on inside. You're taking away the tension. And because there's no tension, then they can relax. But they're not exactly sticking. Depending on which element or compound we're talking about. Well, exactly. Water sticks, but other stuff doesn't necessarily stick. The liquid remains very viscous and doesn't have any tension in it. If you don't change the frequency of a wave, but you change the quickness of the creation of the amplitude, here you go, you change the waveform, right, which is the shape of the pressure variation in the time domain. That's right, that's my argument. Is that, and what a waveform is, though, is a interpretation after destruction. So you basically are interpreting what affects atoms and then reading that on a screen. So you're watching, it's like watching the impact of an electron or the impact of a photon and saying what a photon is. So you've already destroyed the real wave in trying to read it. It's that quantum thing again. You know, you can't, you're not going to be able to retain its, you can't read both, kind of an argument. And so you're synthesizing it on an oscilloscope and saying this is what the wave looks like. Well, it's a synthetic wave. For example, you can have a sine wave, a saw wave, a square wave, and many other arbitrary shapes of waves. Well, I'm going to argue that sound has a shape, and that the ones that make noise that are in the sine wave are likely going to be of high frequency. But again, it doesn't. I don't think you've completed the argument that you can calculate the speed of the achieving of the amplitude, and again make the argument that whatever you show me on an oscilloscope is a synthetic representation and not necessarily the true shape of the wave. A sine wave, in actual fact, could very, very much look something like that. It could have a very steep origin, and you're going to see it as a sine wave after it's been interpreted by molecular interaction. By interaction with electrons that are making up your electronic equipment. After interpretation, you might have a sine wave. But anyway, I'm not saying that I even have to destroy the concept of a sine wave. I'm just saying that you still haven't demonstrated that speakers aren't moving at the speed of sound. The diaphragms on speakers. Going into detail, the maximum speed of a diaphragm is different for different waveforms. No one's arguing that either. I mean, I think it would be obviously that different waveforms would create different diaphragm speeds, and that's what I'm arguing. The actual movement of the diaphragm is limited by its physical properties. Well, duh. It's impossible to create a perfect square wave, for example. Well, a square wave is idiotic anyway, and they're usually made up of, it's usually made up of a higher frequency wave that creates the illusion of a square wave. I don't think a square wave is even, I don't think you can produce one naturally. But regardless, what's my point here? Yeah, so you made my point for me right here. And you basically have said you're not, you tell me, you prove to me that diaphragms aren't moving the speed of sound. And you haven't. So, I mean, obviously I can't, I don't have the instrumentality to prove it either, but I'm saying, you look at him, you're going pretty fast. Yeah, it's going pretty fast. All amplitudes are reached at exactly the same initiation speed. Who said that? Why is that in quotes? All amplitudes are reached at exactly the same initiation speed. I did not say that. Oh, okay. Yeah, but what you did was imply it. Okay, you said that you can take frequency and you can do a calculation based on frequency and tell me how fast the diaphragm's moving. Didn't you do that, shithead? You sat there and you used frequency to say, well, look, a wave at this frequency has to move this fast, and you just measured the entire frequency and said, now that tells me how fast the diaphragm reached its amplitude. And you didn't recognize the fact that that's only for half the wave anyway. If you're going to use all the frequency in a sine wave, the peak amplitude is reached in the first quarter of the time cycle, so you'd have to cut it to 1/4 of the entire frequency. So you'd have to multiply frequency by 4, right? Alright, anyway. I did not say that. I believe I implied the opposite. No, look, you directly said it. Alright, you want me to show you your fucking idiotic math? You sat there and told me, here's a frequency. Here's how fast the speaker moves. It goes 1 millimeter high, that times this times that equals this is how fast it moves. You told me how fast the speaker was moving based on frequency. It was a bogus argument. It was bullshit. I pointed it out, and now here you are sitting there saying you're implying something different. No, that's exactly what you implied. You implied frequency dictated speed of amplitude, and frequency does not imply that. It doesn't dictate that. It doesn't explain that. It doesn't have a damn thing to do with that, actually. Frequency has nothing to do with the speed with which peak amplitude is reached. If you increase the frequency but keep the amplitude the same, again, I argued that point right there. And how exactly do you do that? Yeah, the diaphragm obviously moves faster. Yeah, and it'll move even faster if you just change the waveform. You can also have different waveforms, right? Meaning you don't necessarily have to move a diaphragm according to the sine wave. That's exactly my point, shithead. Exactly my point. Yes, exactly my point. Yes, that's exactly my point. I hope you now understand that air molecules are already moving and bouncing at... Well, this is just asshole bullshit. They're moving at high speeds, but they're atoms, okay? They're single atoms. Obviously, a single atom could probably move very, 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 very fast, and it's not gonna make a sonic boom that anybody's gonna hear, right? Right. And that the diaphragm at the limited diaphragm in this limited example does not have to move faster than the speed of sound in order to make audible sounds. Well, I'm sorry, you didn't demonstrate any of that. It doesn't have to. You say it doesn't have to. I say it does have to. I say it can't make a sound just like your larynx can't make a sound, just like a whip can't make a sound, just like an engine doesn't make a sound, just like nothing else makes a goddamn sound unless some piece of it, some part of it is moving faster than the speed of sound. And you still haven't shown me something that does make a sound that doesn't have a piece of it that's moving faster than the speed of sound. So show me something that makes sound and there's no physical part moving faster than the speed of sound, and then we can talk. Yeah. So, that's probably enough. Don't want to beat to death. So anyway, interpretation, I'm going to have to write down as an interesting word. Because everything's being interpreted, and what's being conveyed across things, it's like... just like this camera and the idea of visual signals. You know, I could hold up 2 fingers and convey the idea of 2, and it's converted, you know, by your brain. And the same kind, there's conversions taking place when you move from one medium to another medium to another medium. You're going to be transferring the signal, like you could put it into fiber optics. You could put the frequency into a light beam and make it travel as light through fiber optics, then convert it back into sound. And all those interactions are on subatomic scales. I mean, obviously the photons certainly are, and their interaction with electrons. And so what I'm arguing is that the shorthand they're working with these interactions are just like Fermi might say about you know, comes in clumps, right? So I'm saying that it comes in clumps. This wave it comes in clumps. So when it's moving, when it's propagating, it's moving as a clump. You know, there's a clump of amplitude and frequency, and that's all there is. Amplitude and frequency. There is no sine wave. There is no there's no wave. There's just a clump of energy imposed at a regular interval called frequency. Yeah. There's a snowball hitting you in the face repeatedly. Yeah, something like that. And the snowball is initiated by atoms moving faster than the speed of sound. Atoms electrically bound, let's say, and that have a significant collective density. You know what the minimum is? I don't know. What's the smallest thing that can create a sound? What's the smallest sound that has any, that can migrate any amount of distance? I mean, it might be interesting to try to figure that out. But not really relevant to the conversation, in my opinion. What's being argued? Clearly, matter moving creates sound. My argument merely is that the matter must move in excess of the speed of sound to propagate the sound wave. The sound clumps. Yeah. Alright, anyway. We'll try again. So anyway, thanks to Hofladay. He did the demonstration. It was sort of interesting with a copper tube and dropping a magnet through it, and the magnet drops through it much slower because of a magnetic field it actually creates by first inducing an electrical field, which is sort of interesting. Yeah, I found it interesting. I have to think about it for a while, but it was very interesting. Never thought about it that way. I mean, I always thought about wires, coils of wires, but I never really thought about the fact is essentially you can actually magnetize the wire, the coil. You don't need the rest of it. The rest of it makes it work better, but it's creating the magnetic field without it. It was very, even in aluminum disc, it was just very, very interesting. Anyway, this is probably enough. There was some other stuff I wanted to get to, but I got to organize it better. So I'll do that next time and such. Thanks you for the comments, but there's still 2 people thumb that up. It's a garbage response. I'm sorry, it's garbage. You didn't prove that speakers don't move faster than the speed of sound. Couldn't prove it. And that's what I need to have proven. I need some example of sound being created by something not moving faster than the speed of sound. Show me something that makes a sound that isn't moving faster than the speed of sound. Show it to me.